to speak to you all. Just open that. Good. The aim of this talk today is to give you a little bit of an overview of how we can use formal methods for assuring autonomous systems. Now, it's worth saying that my presentation, unlike some of the other presentations you will have seen in the S&T training sessions, is a little bit less polished. And the reason for that is I'll just introduce myself a little bit more. So I am a research fellow. I have a fellowship with the UK's Engineering and Physical Sciences Research Council, which gives me a 3-year project. The title of the project is CyPhyAssure, and CyPhyAssure is all about assuring cyber physical and autonomous systems. I've just entered the last year of my fellowship, and essentially what I'm going to be doing today is giving you some of the results that I've come up through my research, and as well give you a bit of an overview of how I see the use of formal methods and some of the challenges as well in that. I'd be very happy for you to raise questions or comments if you'd like during that. I've got the chat window open on my other screen, and I can also see the list of participants, but do feel free to unmute yourself and ask a question if you'd like to. Yeah, otherwise, I'll probably speak for just over an hour, although it might go a little bit longer than that. But yeah, we'll be finished by 12:30 BST. So this is joint work. I'm very grateful to my collaborators, Mario Glacier and Jakub Namushi, who are fellow researchers at the University of York. And also some of this work was done in partnership with an industrial partner called D-Risk. And so I'm very grateful to Colin O'Halloran and Nick Tudor, who are the directors of that company. So I'll make a start. Today what I'm going to do is I'll start off by giving some background and motivation, explaining the reasons why we need formal methods, but also some of the challenges in applying those to autonomous systems and some current technological solutions that have been recommended. I'll talk about my own project a little bit, CyPhyAssure, and some of the technology that we've been developing in that. And then I've got 2 case studies that I'd like to go through with you, one of which is not an autonomous system, but is a secure entry system, and how we have used formal methods to assure that. And the second case study will indeed be an autonomous system, which is an autonomous underwater vehicle, or the safety control of such a system. And then I'll conclude. So first of all, some background and motivation. So we heard a lot about safety engineering and assurance cases already this week. But just to remind you, of course, the objective here is that we can assure that systems provide an acceptable level of safety. And we do that, of course, by determining things like hazards and risks and causes, and try and show that these have been mitigated and come up with safety requirements, which can then be demonstrated using an assurance case. Of course, here we have one of the classic definitions of an assurance case. I'll not go through it with you again in detail, but I want you to remember that one of the main aims of an assurance case is about convincingly justifying, right? So you know what you need to show, but what you need to do is to convince somebody that you have indeed shown safety, right? And that communication aspect is very important. And as we'll see, formal methods can very much fit into this, but we have to be careful when we're using them. As we've also heard, assurance cases are typically presented using visual notations. Goal structuring notation and CAE are the dominant ones, but also there's this standard SACM, this structured assurance case meta model, which is increasingly being adopted and really forms a central part of the research that I'm doing. So we've seen this kind of example of an assurance case before. Of course, we have claims, we have context, we have strategies that allow us to decompose the claims, making use of further context, and so on, right down to where you have your evidence at the bottom. Now, in this case, when we get down to this goal here, hazard H1 has been mitigated or adequately mitigated, we're going to make use of formal verification. And so kind of the starting point for my research was saying, well, how can we actually um, how can we actually make use of a real formal verification tool in this solution? You know, how can we have it so that this assurance case um, is somehow actually performing a verification, right? There's actually a formal model here and a tool that's being run on that formal model to get a verification result. Um, Now, why do we want to use models? Well, this is pretty basic, but of course, we know that evidence from a system, a hypothetical system, before you've built it can be very difficult to obtain. And so typically we want to be able to make use of models so that we can explore the design space and so that we can do different kinds of analyses. So for instance, we might build a small version of a building if we're an architect to subject it to different kinds of forces and see how the model fares. Um, Now, if we do that kind of analysis, then of course it's very important that we remember that that analysis is contingent on validation. You know, there has to be a link between the model and the real world somehow. We have to be able to show that we have taken into account all the important aspects of the real world artifact that we're modeling. We need to make sure that any assumptions that we are making have been explicitly stated and that they can be justified when we actually deploy this in the real world. Um, Now, assuming that we can do that, formal methods bring a lot of benefits. They allow us to have mathematical rigor, so we can provide models which are founded upon very detailed mathematical models. Um, and you can then have the benefit of being able to explore the whole of the state space for the model. Of course, all this is subject to validation, but assuming that you can get that validation, formal methods provide us a way of getting very good evidence. However, as we know, formal methods can be difficult for engineers to use. And so one of the things that we're focusing on in York is how we can use model-based engineering notations in order to make formal methods a little bit more accessible. And I'll be talking about a language in this talk called RoboChart. And RoboChart is a graphical modeling language which we believe allows more accessibility. Another word about issues that you can have when you're doing modeling. I don't know if any of you have heard of this question of practical drift, but I was very, very happy to be speaking after the human factors talk this morning, because of course it's often the case that when we develop systems, how we envisaged the system being used, that how we originally modeled the system being used can deviate over time. And when that happens, you have this issue of practical drift, which is where the system in operation gradually drifts away from how you envisaged the system being developed. And this can be okay. But of course, an issue with this is that if we have used that model to demonstrate safety, but then the real system is no longer conformant with that model, then we have to ask ourselves, well, to what extent are those verification results that I've used as in my evidence, in my assurance case, to what extent are they really relevant now? This is related to the issue of the reality gap, which you may well have heard about. You know, this issue that there is often can be a significant gap between the models that we develop and reality. And this is a well-known phenomenon in robotics. You know, you create this beautiful model, you know, where the robot moves around perfectly in its environment, and then you build it in the real world, and you find, well, actually, you know, the arm of the robot doesn't move as smoothly as we envisaged, or it doesn't quite move at the velocity that we were expecting, and so on and so on. And of course, if this happens, then the results from a predictive model can become irrelevant. You might have heard of this famous quote from George Box: "All models are wrong, but some are useful." And what this is, I think, really showing is that models only they can only be useful in um, giving us a picture of the real world, right? So they can never give you all the details, but they can provide insights. But you just have to be careful when you're using them. to make sure you constantly maintain the understanding of how a model relates to the real world. And of course, this can be particularly a problem for robotic and autonomous systems, where you have a very uncertain environment that you're putting your robot into. Maybe you can't characterize all the assumptions that you think you need. So maybe your autonomous system actually needs to evolve while it's in development. Um, and so one solution that we are trying to develop to this is assurance cases and models as living artifacts, right? So you don't just create your assurance case at the beginning, when you've developed the system, but rather the assurance case remains as a living artifact throughout the life cycle of the system. And in many ways, we view assurance cases as being the kind of central artifact for stakeholders in a system development and maintenance process. So it allows all the stakeholders to communicate with one another and to understand each other and to understand the different aspects of the system and how you have arrived at the safety claims and how you've argued them and so on. This is also, of course, related to to digital twins, right? So the idea that you have a model running somewhere which is enabling you to understand how a system might be deviating from what you originally envisaged. So we're trying to develop that kind of technology, and of course, this is very much related to FANG's research, looking at executable assurance cases. And so by having those executable assurance cases, this would be a way of having these kind of evolving assurance case artifacts. And secondly, from a formal verification standpoint, over the past 20 or so years, there has been a lot of effort in the development of automated verification tools, tools that we can use to check properties of formal models. And not just check them, but recheck them, right, as we're evolving the system. So you can have properties specified in formal logic, you then evolve the model, and then you check them again, and you see, well, do these still hold? And if they don't hold, then that gives you some information about how the system may have deviated, so that you can then make changes, or perhaps you need to revise your requirements, change your assumptions, change your model. But by having automation for this, you can kind of have this loop where you are constantly verifying and re-verifying it for continuous assurance. So back to formal methods. So what is a formal method? So this is quite a broad audience, so I'm kind of starting with as few assumptions as possible. We talked about DO178C earlier in the week, and DO178C has a supplement which is called DO333. Which is the formal method supplement. And essentially what DO333 shows is how you can use formal methods to satisfy some of the objectives of DO178C when you're designing software for aerospace applications. So it has a pretty good definition of what a formal method is. You have a formal model combined with a formal analysis, right? So you've got some kind of modeling paradigm that you're using and some kind of analysis technique that you can apply. So for instance, you might be thinking about something like state machines, and you might be thinking about something like model checking, right? So checking temporal logic properties of a state machine, for instance. So formal methods, as I said, they can bring both rigor, in as much as we can explore, in theory, all of the state space. And one of the nice things about the kind of formal methods I use, which are based on symbolic techniques like automated theorem proving, is that actually you can even explore an infinite state space, right? Which is very important when you're dealing with physical systems based on things like differential equations and so on, and probability, where you have these very, very large state spaces. And so, yeah, by having proof techniques and so on, you can really explore those. You can do so in a very rigorous way. And secondly, of course, automation, as I mentioned, that by making use of automated verification tools and SMT solvers and things like this, we can greatly automate the verification process. So then the questions become, so how do we then make use of formal methods in an assurance case? Of course, formal methods practitioners, we love formal methods, right? We think they're amazing. We think that they can um, model so many things and improve so many techniques, but um, we have this temptation that we want to formalize everything, right? You know, that you want to be able to take all of my assurance case and somehow recast it as a mathematical object, which then means that I can ask any kinds of questions I want to. But I think it's important that we challenge this assumption. You know, should we be formalizing everything? And DO333 recognizes that this is not a reasonable assumption. So there are two objectives in DO333, which are here. So the first of this objective is trying to make sure that you are using an appropriate formal method to meet a verification objective. So it says when formal analysis is used to meet a verification objective, there's an additional objective to ensure that each formal method used is correctly defined, justified, and appropriate to meet this verification objective. Now, what appropriateness means, I guess, depends on the application. But you want to be making sure that it is a formal method which is suitable to show the kind of property that you need to demonstrate. And of course, this isn't an objective that can be satisfied with formal methods, right? This is an argument about a formal method itself, right? And so therefore, we need something outside of formal methods to show this, right? And this is why I see assurance cases are so important, because they allow us to put formal methods in context. It's also recognized by this the second objective here, FM 632A. So this is about showing the compliance between low-level requirements and high-level requirements. And what it says is that formal methods cannot show that derived requirements and the reason for their existence are correctly defined. This should be achieved by review. Right, so you need to have somebody who is checking that your formalized requirements and how you have come about, how you have derived those in the first place, that those have been done in a correct way. And this can only be checked by a human. So yeah, when we use formal methods, we want to be able to, we need to have assurance cases so that we can put the results in context and show that we can review and justify how we have derived those properties. So let's talk a little bit about the formality spectrum then. So there is a spectrum of different kinds of artifacts that we can make use of. Of course, on the informal side of things, we have things like natural language, which is very flexible and of course very good for communication, but can be imprecise or have ambiguities inside of it. Then in the middle, you have what's sometimes called semi-formal, but I prefer the term structured. And we're thinking of things here like UML, where you have a constrained formal syntax, but some or no formal semantics. And these can be very useful, and this is where you kind of want to be able to combine together things that do and do not have a formal semantics. And then, of course, at the bottom, we have the full formal syntax and formal semantics. And sometimes we will want to make use of all of these things in an assurance case. Of course, if we're talking about communication, then we need to be able to have natural language, although sometimes it can be helpful to constrain that natural language. So you have things like constrained natural languages, which broadly correspond to formal notations, and yet they are somehow written in a human readable way, and those can be very valuable. Also, there's various natural language processing techniques that you can make use of, which would allow you to, in some circumstances, deduce from a text some kind of formal formula, which you can then use for formal verification. Right. Certainly, there's three roles for formal methods in assurance cases. So first and most obvious, we can use evidence from formal models and make use of automated verification techniques. We can try and formalize the claims themselves. So in the assurance case examples that we've seen so far, the claims simply have natural language inside of them. But as I've mentioned above, you can use those you can use a variety of formal property languages like first order logic and linear temporal logic and communicating sequential processors, and of a variety of other formal languages to give formal semantics to those claims. And thirdly, you can try and formalize the arguments themselves so that the structure between claims in formal logic. And this is something that's been done quite a lot by people like John Rushby. I've tried to show how you can embed assurance cases into logic so that you can check them. But again, we do need to recognize the partly informal nature of assurance cases. Again, it's about communication. It's not simply about embedding everything into mathematics. Secondly, we need to consider integration of a variety of formal methods, and this is really important actually when we come to autonomous systems. When you come to design these things, you have to use lots and lots of different kinds of notations, and of course you need to use lots of different methods for analyzing those, and yet we need to be able to use them together and coherently. And also, finally, we need to provide accessible notations for engineers to use. So this is really the motivator for my research, right? So I want to be able to make use of assurance cases. I want to be able to integrate a variety of formal methods into those assurance cases. And I want to be able to make them accessible so that we can have this kind of communication between stakeholders, and we can do it in a way that engineers can understand using notations that they're using already, and yet bringing the rigor of formal methods to what they're doing. So now let's go to an example of how we can make use of formal methods in practice. So this example is a quite simple autonomous robot, but still I think very useful to think about. It's called the Athon Tug. Tug is being used in various hospitals in the United States for transporting things around the hospital. So you can see that it almost looks like a cupboard on wheels, right? So inside of here, it can contain lots of different things such as drugs or even food and bedding and so on. And basically what this robot does is someone goes and loads it up with some cargo and then gives it a location that it wants to go to. So it's got a control panel on the front of it here, or not on the front, I think it's on the back actually. I think this is the sensor apparatus here. But in any case, you tell it where to go and it will autonomously navigate from one point to another. It's quite an interesting robot actually because it can also use lifts. There's a very nice video, there's several videos on YouTube of the Athon Tug being used. I won't show them because my experience is that video playing over Zoom doesn't quite work that well, but it's worth looking at these, and it's quite impressive watching this going around. It also does obstacle avoidance, which is very important, of course, for safety. So if someone walks in front of it, it can very quickly detect that and slow down to make sure that it doesn't impact. Now, how does this autonomous robot work? Well, internally, it has a floor map, right? So it's moving around the hospital, and it uses its sensors to do localization in that floor map, right? So basically, what's happened is, so before this robot is deployed, a person will go to the hospital and go around with a very accurate scanner, taking information about the artifacts and the features down the wall of a corridor. And then the tug can use those features in order to allow it to localize itself with respect to its internal map. And it's got quite a variety of sensors on board for doing this. So it has a LiDAR sensor on the front of it. It also has sonar sensors and an array of infrared sensors. Now, I want to focus on the infrared sensors here for a little bit because so the way that it does, so one of the important features of the Athon Tug is a wall following algorithm. Right, so the idea is, of course, what it needs to do at the least, before you even start thinking about obstacle avoidance and so on, it needs to be able to accurately follow a corridor. Right, it needs to be able to move down the corridor and make sure that it's not going to bang into walls and things like that. I mean, that's just pretty fundamental. And it uses its map to do that, and it uses an algorithm called RANSAC. RANSAC stands for Random Sample Consensus, and it's a probabilistic algorithm. And you can see a representation of RANSAC in the bottom right-hand corner there. So the idea is it has these 16 infrared sensors on each side. And as it's going along, it's taking infrared sensor readings. Now, infrared sensors, as you know, are very noisy, or you may know that. They can be very noisy. And so as a result of that, as it's traveling along, you get lots of outliers. Right, you get these kind of noisy samples. And then what you need to do is you need to filter out the outliers and work out where actually is the wall. Right, and what RANSAC does is it's random sample consensus. So it tries to find a consensus based on a number of readings. So I think it takes like 100 readings or something every few. I can't remember. I think it's every second or something like that. Probably less than every second. As it's traveling along, and then it performs small corrections to ensure that it can stay following the wall. Of course, for other kinds of obstacle avoidance, it needs more complex algorithms. But you can see, so if we wanted to think about formal verification of this, we'd of course need to be able to think about formal verification of the RANSAC algorithm. So we need to be able to do verification of probabilistic systems. Now, on the other hand, let's think about another view. So we can think about the geometric view as well of this, right? So you can think about the robot traveling down the corridor as traveling in a geometric space, of course. So here's a visualization of a possible geometric model for a robot. So you've got the position of the robot down here. This is its current heading. And in this case, the robot is actually traveling on a curve, right? So this is a kind of differential drive robot. Yeah, so you then need to model its velocity. You need to be able to model other points in its locality that it needs to be able to make use of. And you need to be able to verify properties like, well, if there's an obstacle out here, does it know that exists, and how is it going to respond to that? Right. So you can see that we've got different kinds of views, different kinds of techniques that we need to be able to apply to this. And now what I'm going to do now is I'm going to give you a couple of examples of modeling languages, modeling formal methods that can be used to tackle this kind of problem. But I think before I move on, I'll just check if anybody has any questions or comments so far. No? Okay. Well, I will move on. The first modeling or formal method that I want to introduce you with is differential dynamic logic. So differential dynamic logic is a deductive proof language for hybrid systems. Right, so essentially the idea with differential dynamic logic is you have a model, and this model is specified using a notation called hybrid programs. So a hybrid program is a mixture of, on the one hand, traditional programming constructs like assignment and sequential composition and conditional choices and so on. So you have those traditional programming operators, but you also have operators for specifying differential equations. So in differential dynamic logic, you can reason about differential equations. You can reason about how different continuous variables are changing with respect to time. And so once you've given your model, you can then use differential dynamic logic to guarantee to verify properties like this. So this is a classical statement in differential dynamic logic. So you have an assumption over here, which is a formula on the initial values of your variables, and you have a guarantee over here, which is similarly a predicate on the values of the variables. And so what this means is that if I assume that my variables satisfy a given property, then after any run of the model, I'm guaranteed to satisfy the guarantee, right? And so this is very useful because we can then use this to verify a variety of different properties. So for instance, we could show that if I have static obstacles in my environment, then a given algorithm, a given navigation algorithm for my robot will indeed satisfy the non-collision requirement. Um, so differential dynamic logic has an interactive theorem prover, which is called Chimera X, which some of you might have heard of. And you can access this online. And what it allows you to do is it allows you to perform deductive verification. So to perform a proof that your model does indeed satisfy certain guarantees subject to certain assumptions. And it's important to emphasize again that using this deductive reasoning, you can do prove properties about infinite state hybrid programs. And of course, ordinary differential equations, they are infinite state by their very nature, and uncountably infinite indeed. So down here we have the differential equation that represents the behavior of the robot in its environment. So you say you give the derivative of p, the derivative of the speed, which is the acceleration, the derivative of the, what does this represent? This represents the heading, and then you've got various things to do with angular velocity and how those are changing with respect to acceleration. So you can encode this into Chimera, and then Chimera has this nice technique which is called a differential induction. And the key thing about differential induction is that it allows you to reason about differential equations without the need for symbolic solutions. So typically the way that you will prove something about a differential equation is by handing it over to something like Mathematica, or some other computational algebra system, and asking for a symbolic solution, which you can then try to verify. Now, sometimes differential equations don't always have solutions, and so the advantage of differential induction is that it avoids the need for those symbolic solutions. And so, yeah, Chimera is a very powerful tool which has been used to verify a variety of autonomous robots. The controller algorithms for those. And it can be used in two ways. So on the one hand, you can use it for verifying the controllers themselves. But secondly, you can also use them for deriving safety monitors. So they have this nice framework, which is called the verify pipeline. And what the verify pipeline allows you to do is to derive a safety monitor from a given model that you have verified some properties of. So the idea is you come up with a model of your environment and parameters on the safe behavior of the robot, and then you use the verify pipeline to show that you're verified, to derive code for a verified safety monitor from it. I'm not going to say much more about Chimera X and differential dynamic logic, but if you'd like to know more about this, there's a very good book. So the guy behind this is Andre Platzer, you might have heard of. So he's at Carnegie Mellon University in the United States, and he's written a good textbook on it called Logical Foundations of Cyber-Physical Systems. So if you want to get into verification of autonomous robots, this is a really good starting resource to understand about that. And so you can see on the cover there, they're illustrating the verification of TCAS-like algorithms, right? So where you've got a plane where you're trying to avoid potential collisions with other planes around you. So that's a good resource to look at, I think. So a second example of a formal method for robotics is the RoboChart language. And this language was developed at York. It's a graphical language for describing robotic controllers. It has two principal notations. On the one hand, it has an architectural language, which is a kind of block-based language where you have blocks, and these blocks can have connections coming into and going out from them, representing possible communications. And so the idea is you an autonomous robot, you have several different controllers, and these controllers communicate with each other via these ports. And you also have a representation of the hardware. So the robotic platform, as it's called, that allows you to represent things like your sensors and actuators and how you're going to communicate with those. On the other hand, it has a state machine language, which is similar to UML state machines. So you have states, and you have transitions between the states, and those transitions can have conditions on them. So you have so each of your state machines has a number of variables associated with it, which are given here. So in this case, so this state machine is representing a kind of decision mechanism for a gas detection robot. And the idea is you've got this robot which is moving around an arena looking for hazardous substances by using a gas sensor to check the reading. And so the idea is you start off in this state, no gas, you then input some gas. So this statement here means that we're going to input a value GS, which is going to get placed into this variable, over the channel gas. So you see over here we've got this this event on the interface here, which of course you could then connect to other blocks externally. So you input this reading, you then perform some analysis on it. So if the analysis says no gas, then you just go back to this state. If on the other hand there's something different, you need to check the intensity. If the intensity is high, you're going to stop, right? So then you enter the final state, which means that you've stopped. On the other hand, if it's not too intense, then you're going to go back and take another reading, right? So this kind of notation. So there's an Eclipse-based tool for this language called RoboTool, which has been developed at York. And this supports a variety of different formal analysis techniques. So you can do model checking on these languages. So there's a couple of model checkers which we can support. So on the one hand, there's something called FDR, which is a model checker for CSP. So underneath this has a semantics in the CSP process algebra. We can then use that for verifying properties like deadlock freedom, but also more specific requirements as well. RoboChart is also probabilistic. So you may remember when we talked about the Athon tug, I said that the ransack algorithm is probabilistic. And so one of the things we've been doing recently is trying to model ransack in RoboChart. And the way that this is done is RoboChart also has kind of probabilistic choices in it. So it's not shown in this example, but you can have the option of having a particular kind of node where you go into the node and then you have to make a probabilistic choice to choose where you're going to go afterwards. And this allows us then to do to specify systems which make probabilistic choices. And then we can use the Prism model checker. If you've heard of Prism, it's a model checker for probabilistic and timed automaton. And we can use that then to verify systems with probabilities. And finally, we can also use theorem proving. And so the disadvantage of model checkers is that you have to minimize the number of states that you're going to deal with. And that's because you have this issue called the state explosion problem. But for theorem proving, you can deal, as I mentioned, with infinite state systems. And so you can also take a RoboChart state machine and translate it into Isabelle for the purpose of verification. Now, what we've done is we've looked at here at two different notations, right? We've looked at differential dynamic logic on the one hand, which allows us to deal with dynamical systems. And we've also talked about RoboChart, right? So this language for specifying robotic controllers using state machines. The question is, how do we think about integrating notations like this, right? So as I said at the beginning, when you're dealing with autonomous systems, you're likely going to be having to deal with a lot of different aspects of the system, right? So this is illustrated here. So you can imagine that when you develop your system, you have to make use of lots of different notations. So of course you have to deal with differential equations because you need to be able to model the environment. But you do want to be able to have architecture, of course. Sometimes you want to be able to make use of control laws. So over here, this is a language called Medallica. Modelica is a language for modeling control laws and dynamical systems. And it's similar to Simulink, if you've heard of Simulink. So you have these blocks, these take inputs and they calculate outputs, and so you can kind of connect these blocks together to describe things like PID controllers, which are commonly used in for like matching a set point, a velocity set point, or a heading set point, or all these kinds of things. Of course, we want to be able to deal with things like state machine notations and code on the other hand, right? So we need to be able to have C code for some parts of our artifacts. We might have real world data. We might have formal models in other languages as well. So this is a language called VDM over here. So VDM is a formal language for specifying controllers. And so the question then is, how do we deal with this kind of diversity of notations? How can we bring all of these things together so that we can do verification of very heterogeneous systems like autonomous robots and autonomous systems? And this brings us on to the topic of integrated formal methods. So integrated formal methods, a definition, is the consistent and coordinated use of several heterogeneous formal methods at various stages of the engineering life cycle. So this idea isn't new, but it becomes particularly important when we consider robotic systems. So the idea of integrated formal methods was, I think, originally coined in the 90s, perhaps by this famous formal methods survey by E.M. Clark, where they said that given that no one formal method is suitable for describing and analyzing every aspect of a complex system, a practical approach is to use different methods in combination. Various people have, other people have studied this, and indeed there's actually a series of conferences called IFM, named after integrated formal methods, where lots of people have been looking at this. And more recently, there was a survey done by Matt Lecoq, where he pointed out that robotic systems are inherently hybrid. So as we've been saying, they use lots and lots of different kinds of notations together, and therefore we need this idea of integration. This is an excellent survey, by the way. So I've got a citation to it there. It's an ACM Computing Surveys. We'll say a little bit more about it in a minute, but it's really very helpful for understanding this problem. With a co-author, with my co-author Mario Glauscher, we've also written our own survey, which is also looking at this question of applying integrated formal methods to autonomous systems. So we see this as a very significant issue and something that we'd like to be able to solve. I'm going to pause for a minute because I can see from the chat, sorry, I didn't notice those earlier, but I've got a couple of questions there which I'm just going to address. Okay, so Richard is asking, could RoboChart also be used for traditional systems? Is there any reason it needs to be autonomous robotic? Indeed, so yeah, RoboChart can be used for any kind of system. So the reason that it's called RoboChart is because it's specifically tailored to robotic systems. So it has this idea of a robotic platform where you characterize where you have sensors and actuators and other ways of being able to relate to an external model. And at the moment, they're working on this kind of hybrid integration as well, where you'll have a model of the physical environment that then you'll be able to connect your robotic controller to. And as well, they're connecting it to robotic simulators, so that you can take a RoboChart model and simulate it in a robotic simulator. There's a few of these different simulators. There's one called VREP that they're connecting to, and so that's kind of the aim of it. But sure, absolutely, the core language of state machines, it doesn't have to be applied to robots. It is more general than that. Does that answer your question, Richard?
Yeah, so, and it sounds like it's more robotics rather than autonomy necessarily. It's focused on enhancing the modeling for the robotics bit. Is that fair to say?
Yes. At the moment, so it's more looking at robotics. So yes, so they say autonomous and ground robots is kind of the focus. Sorry, autonomous and mobile robots. So yeah, not necessarily autonomous systems. That's right.
Okay, thank you.
See, I've got a second question from Vibhu. I'll just read it out. So how do you handle complex distribution? And when I compare it to a reference probabilistic ML, the biggest challenge in both learning and inference is the convergence of such distribution, a closed form solution which never exists. So how do we build formal verification on approximate inferences? Excellent question, Vibhu. I'd love to talk to you about that in more detail. The straight answer is I don't know at the moment. So we're kind of right at the beginning of looking into verification of probabilistic systems, and it's a very young area in general. So Andre Platzer has got an extension of differential dynamic logic called stochastic differential dynamic logic, which allows you to deal with these things, but it doesn't have an implementation at the moment, and it's very much in in the early stages. Yeah, perhaps you had more comments you'd like to make, Vibhu?
Hi, Samin. Thanks for your explanation. I mean, exactly, that's one of the challenges, and that is one of the core pain points in any of these complex. For example, taking neural network. In a way, we are learning a complex distribution, but while we are learning, everything is approximated. Nothing is like old school differential equation where you have a fixed result and fixed answer where you can apply these form. I mean, I have not been gone in detail of formal verification, but as soon as we enter this approximate techniques or proximate inferences, everything blows up. And what do you suggest? Exactly, I know it is very new, but is there something people are working on? I've seen something like Reluplex, which was a formal verification for neural network, but that is for classical neural network, not something which can be generic enough. So yeah, please go ahead.
I'm afraid I was going to precisely point you to Reluplex because so the latest thing that so actually there was quite a good presentation at last year's Integrated Formal Methods Conference that happened in Norway in December of last year, which was kind of conducting a survey about that. I'm afraid I can't remember what the speaker was called though, but Vibhu, if you drop me a message or an email at the end of the presentation, I can look that up for you. But yeah, I'm afraid it's an area very much in its infancy at the moment, and it's not one that I would be I would be able to comment on further, I'm afraid.
No problem. Thanks a lot.
Okay, but thank you. But good questions, and thank you. It's good to get some feedback. Okay, so Lookup's survey, as I said, I think it's very helpful. So one of the core results of this was a survey of 63 papers, which are looking at verification for autonomous robotic systems, and they kind of look at the different tools that people are using, right? So on the one hand, they look at model checkers, so things like Prism and Spin and UPAL. I guess we've heard of some of these, and they look at the references and things being used. They look at theorem provers as well, so Chimera I've already mentioned. They don't mention Isabelle because at this point Isabelle hadn't really been used that much for verification of robotic systems, but that's something I'm working on at the moment. And they talk about other things like Alloy and Z, right, and so on. And so lots of people are using lots and lots of different notations. So this is a very good starting point. So if you want to get into formal verification for autonomous robotic systems, I highly recommend this survey. It makes for a very good read. And again, basically the point that they come to at the end is, well, in order to do assurance for these very complicated systems, we need to be able to work out how we can compose these different aspects together. And this idea of integration is really of great interest to me. I think it's a very big question. And what I'd like to do is I'd like to suggest to you a solution. It's not a universal solution, but it's one that I've had some success with in my research. And just to outline the challenge, how do we classify and relate all of these different formal techniques? Can we think of core principles that unify them? Well, I guess we can, right? There are different paradigms, of course, that we use in verification. Because we have concurrent systems, systems that communicate with each other. and run in parallel. We have mobile systems, we have real-time systems, hybrid systems, probabilistic systems. And how do we go and link and integrate these various formal semantics, given that they are so different? And as a bigger question that I'm interested in, how can we use them together? How can we build an assurance case? How can we provide tools for those assurance cases that can make use of lots of different analysis techniques together, and can automate the execution of those techniques so that you can be constantly checking and rechecking the evidence? Now, if we can do this, aside from being able to do these kinds of very complex assurance tasks, we can also build, we can find ways of constructing correct program analysis tools in a modular way, or relating them in a modular way by thinking of these different aspects. And so a potential solution to this is a semantic framework called Unifying Theories of Programming. It's actually a very old idea. There was a book written in 1998. You might have heard of Tony Hoare, quite a famous computer scientist. Less well known, but also very talented, is Professor He Jifeng, who is at East China Normal University in Shanghai. And they together developed this framework, UTP, as a way of integrating heterogeneous formal semantics. So let me talk you through the three words. Unifying. Well, of course, we need ways of integrating different heterogeneous languages and notations. Theories. Well, how are we going to do that? Well, we need to consider these different languages at the theoretical level by considering the computational paradigms that underpin the various notations. Right. So understanding these building blocks, right, that we need to be able to connect together and relate to one another, so that we can put together these different bits of evidence and make sure that we do have a coherent argument. Programming, perhaps the most controversial. So we're looking at notations that can be executed by a computer. So it's worth saying this is not only about programming languages, although that was originally what it was targeted at, but our research has indicated a wide variety of modeling languages can also be included in this framework. And so what I've tried to do here is to sort of visualize the idea behind it. So you kind of have this sort of semantic stack. So on the bottom, you've got unifying theories of programming. And what this allows us to do is to describe these different building blocks, right, to put down foundations for our verification tools and to understand how they relate to each other so that we've got a foundation on which we can build. We can then use those theories to develop what are called denotational semantic models. So denotational semantics is a way of giving mathematical semantics to the constructs of a programming language so that you can reason about them in terms of things like relations and arithmetic formulae and so on and so forth. And then on top of your denotational semantics, you can build other kinds of semantics like axiomatic semantics. So things like Hoare logic, separation logic, rely guarantee calculi, assume guarantee calculi, weakest preconditions, dynamic logic, and so on. So these are all axiomatic semantics. So these are different logics that we can use for reasoning about programs and models. Then we have operational semantics that allows us to of course, execute notations, and algebraic semantics that allows us to write down algebraic equations about different constructs. From this, we can build automated verification tools. And this then allows us to be able to think about how we can unify together all of these different notations in a coherent framework. And this is what unifying theories of programming is all about. And in the rest of the presentation, I'm just going to give a couple of case studies of how we have applied this, and also an implementation of assurance cases in Isabelle. But before I do that, I can see I've got another question on the chat. So I'm just going to look at that. So it's from Raoul. Okay, I think that's more of a comment pointing to a paper. So thank you for that, Raoul. Did you have a particular question or anything else you'd like to say to me?
No, no, no. It was just an answer for Vibu, just to help him with this question.
Great. Thank you very much for that. That's a helpful comment. Oops. Okay, so what I'm going to do now is I'm just going to very briefly take you through the technology that we've developed as part of my fellowship project, CyPhyAssure, and then I'll show you these two case studies, and I've got about 35 minutes left, so I should be able to do that in time. Okay, so there's kind of two key artifacts that we've developed on CyPhyAssure. So Fang earlier in the week talked about SACM, Structured Assurance Case Meta Model, and so what I have done on CyPhyAssure with my my colleague Jakub Namucci is develop a plugin for a tool called Isabelle SACM. I'll say more about this in a minute, but the idea is that this is a machine-checked language for SACM. And then we have integrated formal methods, which is the second of the two artifacts, which is called Isabelle UTP. So the idea is that you have a graphical tool for describing assurance cases at this level that an assurance engineer is making use of. And then this is going to be translated into some kind of machine-checked language in Isabelle SACM. And this is going to make use of artifacts from Isabelle UTP, which are these kind of different heterogeneous formal semantic models. So let's look a bit more about how this works. So just a bit more of a word about SACM. So SACM is an OMG standard meta model for model-based assurance cases. So the way I think the best way to view SACM is that it's an endeavor to unify and extend established notations like GSN and CAE. So I don't view as SACM as somehow being in competition with these notations, because SACM is a meta model, right? Whereas GSN and CAE are both graphical ways of representing assurance cases. Now, that said, there are things that you can represent in the SACM meta model that you cannot represent in either GSN and CAE. And this is because Tim Kelly and others, when they were working on SACM, realized that there were some shortcomings of GSN that they wanted to be able to deal with. Nevertheless, in terms of thinking about this in a formal methods way, we can see SACM as a conservative extension of both GSN and CAE. And therefore, you can always take a GSN diagram and represent it in SACM. And indeed, we've got a tool that is being developed at York, which does just this, right? So you draw GSN, but underneath SACM is being generated. The main concepts which you use in SACM are terminology, so definition of terms and categories, argumentation, of course, where you break down claims into subclaims, strategies, and evidence, and artifacts, so evidence to support claims and traceability between those artifacts. It provides more precise categories for claims, so you can have things like assumed claims, which are going to need to be satisfied somewhere else in the assurance case. You've got axiomatic claims, which are things that you're just saying, well, this is just axiomatically true, so I'm not going to try and support it. But you also have things like defeated claims, because SACM is also supposed to have this idea of dialectical argumentation, where you can actually challenge an assurance case and you say, well, does this claim really stand up? I'm going to present this counter evidence, which is going to allow me to defeat this claim, so that you can then engage in this argumentation to try and strengthen the assurance case, right? And that then allows you to have a good meta argument for why you should trust your assurance case. Now, the particular reason, one of the main reasons I'm interested in SACM is because it gives us greater opportunity for integration of formal methods. And one of the reasons for this is, well, two reasons. So first of all, artifacts, because you've kind of got this explicit artifact meta model, you can link to all kinds of different artifacts. And of course, those artifacts can be different formal analysis techniques, which is great, which is really helpful. But you can also have traceability. So you can say things like, well, who created this model? How did they create it? You know, what were the artifacts they used to develop that? What tool did I then use to analyze this this artifact and produce this evidence, and so on and so forth. But the other thing is, in the terminology package, you can have things like structured language, and that structured language then provides a way into formal methods, right? So that you can have things like logic statements which accompany your claims, which you can then use for the purpose of verification. Now, again, this is all it's all very important that these things are validated, right? That you don't just write down logic statements, but that you actually explain what it means and provide a justification for why you formalized it correctly. But the great thing about SACM is it allows you to do all of that and a lot more as well. So I think it's a very good standard to look at if you're not aware of it or not using it already, but you're working with assurance cases. I really encourage you to look at SACM. Now I'm going to tell you a little bit about the main tool that I've been using for this work. So you might have heard of Isabelle. So Isabelle is well known for being a generic proof assistant. So it's a tool which allows you both to do proof, but also automate. So check proofs, but also automate proofs. So it has a variety of different automated proof techniques inside of it. It also has integration of automated theorem proving and SMT solving. It's what's called a foundational proof tool, which means that all of your proofs ultimately boil down to a small core of logical axioms, as you do in mathematics. And this is quite impressive, actually. So, for instance, Isabelle has a very good implementation of multivariate analysis. And we use that multivariate analysis package to do verification of hybrid systems. But ultimately, things like limits and things like differentiation and integration, they all boil down ultimately to set theory inside of Isabelle. So it's kind of built in this sort of layered mathematical approach, which is quite nice, really. But what Isabelle has famously been applied to lots of automated program verification projects. So you might have heard of the SEL4 microkernel verification. So this is a secure microkernel that was verified. And also there's a real-time operating system called PikeOS that was also formally verified using Isabelle. And these are pretty big projects. So they show that Isabelle really it really can be extended. It really scales to larger projects. So you've probably heard about the program verification side of things, but what you may not have heard is that Isabelle also provides a lot of other features. It has a machine check document model with an extensible parser. And it also supports both formal and non-formal content these days. So of course you can write comments on a program, which would be non-formal content. But Isabelle takes this to a much higher level where you can actually have whole commentary, marked up commentary with links to formal entities within it, so that you can explain what a definition means and how it uses other definitions and so on. And you can take an Isabelle document and put it through a document preparation system and produce a PDF from it, which has been checked by the logic engine and then provided in an accessible way. And so in many ways, I view this as I think this is a good tool for trying to do assurance cases. And so this was kind of the starting point for CyPhyAssure. You know, can you use Isabelle as a way of representing assurance cases with formal evidence inside of it? So one of the results that we came up with from this was this tool, Isabelle SACM. So this is a textual interactive assurance case language based on SACM. It allows us to embed arguments into Isabelle with verification evidence. Now, it's important to say that when I say embed, I don't mean embed into logic, right? We're not necessarily talking about the kind of John Rushby idea of taking an arbitrary argument and somehow embedding it into logic. Rather, what we're talking about is using structured informal artifacts to provide commentary on formal artifacts and use those formal artifacts as evidence and context and so on. So we're not forcing the user to write down formal formulae and so on, but you have that option should you want to. So this is how it works. So on the left, we have a kind of small example of an assurance case. And on the right, we have the representation of this in Isabelle SACM. So you have a sequence of commands, and each of the commands represents one of the elements of the assurance case. So claim C1, the system is acceptably safe. Claim C2, all identified hazards have been mitigated. And then you have an inference, and the inference shows that C1 is going to be supported by C2. Then we have some context over here, so you're going to link together these things, and so on, right? So Does someone have a question? No? Um, so the idea is that you draw this in a graphical assurance tool, and then you have the mapping from this into Isabelle, and that then allows us to check various properties of the argument in the formal tool and link them to formal verification evidence. So how does the linking work? Well, in Isabelle, you have this idea of an anti-quotation. So you see these funny at, open brackets, close brackets things. So what this allows us to do is to insert a formal link to something that has previously been defined. So for instance, here, this inference is going to link to this claim C2. And so this will then have a hyperlink so that you can click on this and it will take you to that claim. And likewise for this one. But we can link to other things as well. So here we have, we're linking to the hazard log as part of this. So this is essentially unstructured text between these quote symbols, but you have the option of adding links to formal entities described in the document model. And indeed, we can link to other things like formal verification results, which we're using here. Right. So this then allows us to have assurance cases in Isabelle, which have formal evidence associated with them. And then in terms of how do we then integrate together a variety of formal methods? So we have a tool called Isabelle UTP, which have been under development for about the last 5 years. And this implements UTP on top of Isabelle so that we can provide verification tools for lots of different kinds of languages. And just as a couple of examples of that, so that we can take the RoboChart language, and we have, again, this kind of textual representation of RoboChart in Isabelle, which is, again, machine checked. So each of the states is going to be translated, and each of the transitions. And underneath, this generates the formal semantics inside of Isabelle, and which is checked for well-formedness. And so it's a dynamic semantics. So it's written using a notation called reactive programs, which I'm not going to talk about in a lot of detail. But the point is that you can then subject this to automated symbolic verification. So you can check for deadlock, you can check for other kinds of requirements. And of course, because this is a symbolic entity, infinite state systems are not a problem. And in terms of Isabelle SACM, we can link to different elements of this from Isabelle SACM. So for instance, I can say that one of my transitions might provide evidence that I've satisfied a given requirement, or one of my entry actions. We'll see an example of this when I consider one of the 2 case studies. And just to illustrate the kind of integration side of things, we also have an implementation of differential dynamic logic on top of Isabelle UTP. And this allows us to verify hybrid systems using ordinary differential equations and so on. So therefore, with Isabelle UTP, we can use notations like RoboChart and differential dynamic logic together. So then in, I guess, the final 20 minutes or so of my talk, I just want to briefly take you through these 2 case study examples of how we have applied Isabelle UTP and Isabelle SACM together to produce assurance cases in Isabelle. So this first example is not an autonomous system. It's a secure entry system. So Tokeneer, it's called, is a famous assurance demonstrator that was developed in the 90s. So it's a system for guarding entry to a secure enclave, which was developed by the NSA. And a company called Praxis, who are now Ultran, were tasked with assuring it up to EAL5 of common criteria. So common criteria is one of these international standards. It's a standard for showing security properties. And EAL5 is the second highest level of assurance. Now, it's worth saying that they believe that they could have got to EAL6 with additional proof support. Now, this was in the mid-90s, so automated formal methods tools weren't so prevalent at the time. Now they are. And so in our work, what we've done is we have taken the verification, the formal functional specification that they developed in Tokeneer, so their formal model, which is a state transition system, which I'll say more about in a minute, and mechanized it in Isabelle UTP and proved formally some of the security properties, and mechanized an assurance case, making use of that formal verification evidence. So just to tell you a little bit about how this works. So Tokeneer has a main component which is called the Tokeneer Identification Station, the TIS. It has several peripherals on the outside. So crucially, it has a token reader, which is a card reader, and it has a fingerprint reader. So the idea is that somebody approaches the secure enclave and they want to gain access. They need to present their smart card, but they also need to take a fingerprint. And so the objective of the TIS is to determine under which circumstances a user can gain entry and deny entry to users that don't have appropriate privileges. So what happens internally is that the token contains several cross-check certificates and a fingerprint template. And the TIS checks that all the certificates cross-check against each other and that they're valid and so on. It takes a fingerprint, which it checks against a fingerprint template within the card. And if everything is okay, it will unlock the door. And so you can imagine this is an important system. It's a process that you really want to make sure works correctly. And so what they did was they developed a formal model of this in the Z notation. They had a number of security properties which came from the security target under common criteria. They proved that the formal specification satisfied those properties. They then refined that into a formal design. So this is a highly abstract representation of the TIS, whereas this is a much more concrete one, which is much closer to code. So they had a refinement proof for that. And then ultimately, what they did is they had an implementation of the program in Spark Ada, which they then verified against the formal design, which then by transitivity ensured that the security properties were therefore satisfied. And they did static analysis of the Spark implementation to make sure that it was indeed a correct refinement of the formal design. So this was kind of their overall argument for how this worked. And so then you had code that you could execute that ultimately was formally verified against the Z specification. So just to give you an impression of how this is quite a significant benchmark, quite a significant example. So this is one of the state machines. So it's a state-based model. So you start off in this state over here, quiescent, where you're waiting. You then read a user token. You then check whether you need a biometric check or not, because once you've gained access once on a particular day, it won't take the biometric check again. It will just allow you entry. And so it first checks whether it's required or not. And also you can fail at this point. If it is required, it will wait for the finger, it will read the finger, and then it will update the token, and then finally it will unlock the door. Right. And this is only part of the state transition system. It's actually much bigger than this. And so it's quite a significant model. And it has a number of security properties, as I mentioned already. I won't go through these in detail because I don't have time. But essentially, we'll look at the first one. So the first one is really ensuring that the user token has the appropriate certificates on it. So you have to have an authorization certificate and 3 other certificates called an identity, a privilege, and an identity and authorization certificate, which cross-check against each other, and a fingerprint. The alternative way that you can gain access is if you're a particular class of user called an admin, in which case you can gain access provided you have the role guard, which means you can override the security mechanism and get in. And so basically what they've done is they show that they formalize each of these security requirements and then provide a proof that the Z specification satisfies those, and therefore by showing that the code is a refinement of the Z specification, you show that it also satisfies the security properties. So in our work, what we've done is we've mechanized TIS in Isabelle UTP. It's worth saying that this is a quite significant model. So it's got 60 plus variables, 100 plus operations, which are the transitions, and 30 plus invariants. And we can then do automated formal verification of the 3 security properties. And this depends on the addition of some invariants which weren't found in the original documents. And the reason for this is because they never had a mechanized proof of the safety of the TIS. So this is something that we've added in Isabelle UTP. And then what we can do is we can integrate this all together in Isabelle SACM. Now I'm going to move on from this because what I really want to get to in the last 10 minutes is a case study of an actual autonomous system, which is an autonomous underwater vehicle case study, which is being developed in collaboration with DRISC. So I don't know if you've heard of BlueRov, but BlueRov is an open AUV platform. So it's a tethered, remotely operated vehicle. I think it costs like £5,000 or something like that to buy. And so DRISC, who are a company based in the UK, are trying to develop a safety controller for this. So there's a consortium which is trying to show how you can use such a system safely for underwater maintenance tasks. The AUV can either be under operator control or it can be autonomous. And basically the autonomous behavior is waypoint following on the one hand, and on the other hand, it can perform various maintenance tasks as well that you can give to it to do. It needs to be able to demonstrate regulatory compliance, which is why DRISC are very interested in having an assurance case for this. And so the kind of hazards that you're talking about are, of course, collisions with static and dynamic obstacles, such as other vehicles. And also in this case, they want to avoid things like splash. So you need to be able to show that the AUV doesn't autonomously emerge from the pond. So that has to be done under operator control to make sure that that is mitigated. So DRISC supply us with some system safety requirements for this. I'm going to skip over some of the details, but the component that DRISC are developing is called the last response engine. So this is a safety controller for the AUV. And so it assures safety in the presence of non-verified components. And it operates in 4 modes. The operator can be in control. It can be in main operating mode, meaning it's got its normal autonomous behavior. It can be in high caution mode, or it can be in collision avoidance mode, meaning that it's avoiding a potential collision. And so what we're trying to do in this project is to support the development of certified software under DO 178C. So you have a number of requirements, most of which I'm gonna skip over. But they are things like when and only when in operator control mode, the LRE shall accept operator control inputs and send them to the autopilot. So the next slide, I think, has got the architecture of the AUV that we've developed. So this is in the RoboChart architectural language. So you have a robotic platform, which has got sensors and actuators. And then you've got 3 main controllers. So you've got the operator, you've got the LRE, this safety controller, and you've got the autopilot. And so the idea is the LRE doesn't directly control the sensors and actuators, but there's a second component, this autopilot component does that. So this would probably be some kind of PID controller. And the operator has the option of controlling should it need to, and it can request that the AUV switches between different modes. So these represent events that the operator can send to the LRE to give it different commands. So let's look at how the LRE works. I'm going to skip over this slide, but just to say we have this kind of formal language in Isabelle that allows us to represent the different variables that we have in the state space of the AUV. So these are things like the depth below the surface, the north-south velocity, the east-west velocity. And one of the things that we've done is we've extended Isabelle with support for the SR unit system, so that we can have things like meters and meters per second, as well as numeric data types, which then allows us to have a sort of extra level of rigor for formal models for physical systems. And also we have this kind of requirements annotation language so that we can say that this is somehow satisfying one of the requirements. So how the sensors should be formalized and the kinds of information that they convey. We then have a state machine, which is here in RoboChart. So let me give you an example of one of the transitions. So we start in operator control mode, and we can transition, and the operator can request that we go into main operating mode using this transition here. So this transition says if we receive the event rec MOM, which is the operator requesting that we go into main operating mode, then we have to satisfy these given predicates. So the velocity must be low, and this is just to make sure that we're not driving quickly towards an obstacle or something like this. We have to have a certain distance between both dynamic and static obstacles, and we mustn't be in something which is called an object proximity exclusion zone. So this is a particular area where the LRE, the AUV is not permitted to be autonomous. And provided that all of those things are satisfied, we can go into main operating mode. Now, each of these transitions actually corresponds to a requirement in the de-risk supplied system requirements document. And so one of the things that we want to be able to do in the assurance case is to show that each of the requirements has been satisfied by one of these transitions. What we can do is we can take that state machine and we can translate it into Isabelle, which allows us then to verify it using the notation that I showed you at the beginning. But what we can also do, and this is kind of putting everything together that we've been talking about so far, we can use Isabelle SACM together with Isabelle UTP to show that some of the requirements have been satisfied. So let's look at this example as the last thing. So the requirement that we're looking to satisfy is this one, main operating mode maximum speed, which is saying that on entering main operating mode, and we're using this kind of formal term annotation, so this term has been defined somewhere else in the document. The LRE will advise a maximum speed of 1 meter per second. And this is a formal Isabelle term, right? So 1 meter per second. So this is an SI quantity. And then how are we going to show that satisfied? Well, so we have a claim over here, which is saying that this requirement over here is going to be implemented by the entry action of the state LRE BH.MOM. Right, so this is LRE BEH, and here is the state, and you can see the entry action here. It sends to the autopilot, so it advises velocity of 1 meter per second. And so it's then clear that this particular claim is satisfied by the formal model. So here we see we can use both formal artifacts in Isabelle together with assurance claims to substantiate them. And we can also do verification of the LRE again. So here we have a deadlock freedom proof. And so, yeah, we can verify this even though it's infinite state using symbolic theorem proving. Great, so I guess I'm almost at the end, so I'm just going to conclude. So what I guess I want you to take away from this, I think there is a need for formal methods in assurance cases. But it's important that formal models, of course, must be put in appropriate context. And so that's why we're developing these two pieces of technology together. And of course, we want to be able to provide diverse and accessible notation. So what we envisage eventually is having a kind of graphical model-based tool where you can draw assurance cases and also linked to a variety of other artifacts in graphical notations. And under the hood, you can be generating Isabelle code in the background that you can then use for verification and so on. Now, the advantage of doing all of this in a language like Isabelle is that we can support things like evolution, right? So because in Isabelle, if you change an artifact, Isabelle will check to see what effects that has, right? And you can relay that information back to somebody to say, well, okay, you're going to have this problem in your assurance case. One of your formal verification, if you change a model, one of your formally verified results might change. And so, again, this is all useful for sort of being able to evolve and check as you're going along. So we demonstrated Isabelle SACM and Isabelle UTP, and we gave 2 case studies on Tokeneer and the AUV. Now, I recognize there's a lot to take in there. So first of all, I'd just like to give a vote of thanks to the Engineering and Physical Sciences Research Council that have supported this research. If you'd like to know more about my project, there's a link there. And as I say, it's a lot to take in. So there's a number of publications that we can point you to. So, so the RoboCalc project, which developed RoboTool and the RoboChart notation, there's a link to that there. And there's a number of different publications which we've written about Isabel UCP and about Isabel SACM and applications to the AUV, and also about the different aspects of verification that we've developed. Good, so that's the end of my presentation, and I'd be very happy to take any additional questions.
Hello, everyone. So thank you very much, Simon, for this interesting presentation, this training session. I'm leaving the floor to everyone. If there's a question, you can ask them, maybe through the chat, or otherwise you can unmute yourself and ask the question directly to Simon.
Hi, Simon. Thank you very much for the presentation. It was very interesting and insightful. One question: why did you select Isabel as the theorem prover as your foundation of your work, and not any other model checker that's out there? Because I think the deadlock checking and other things you showed could also be done by model checkers, right?
Yes, so that's a very good question, and I'm sorry I wasn't quite clear about that in my explanation. So the way to view Isabel from our perspective isn't as a particular verification technique. Rather, the way that I use Isabel is kind of as a tool integration framework. So I should have said that. So Isabel is a kind of plugin oriented system that you can plug different tools into. So for instance, you can make use of external automated theorem provers and SMT solvers. You can also make use of model checkers and counterexample generators and so on. So I'm not really putting Isabel in competition to other model checkers and so on. Rather, it's a way that we can access different tools and bring them together under one framework. So thank you. That was a very good question.
Thank you very much for the explanation. Okay.
Are there other questions from the ESRs or other participants? If that isn't the case, Simon, thank you very much for this very nice presentation, the nice introduction also to the formal verification. You also give a very clear view on the different tools and different guidelines where we can start to go deeper in this topic. It was a lot of information in just an hour and a half, so thank you for that. But it was very useful.
Thank you. And if anyone would like to email me or contact me about any aspect of this, do let me know. As I said at the beginning, you know, this is not polished research at all at this point. These are very new results, and I'd be very interested in seeing if there are opportunities for collaboration between my project and any of the ESRs here today. So there've been some good questions, and I think there's some good research questions for the future, and so do approach me about them. I'm very happy to talk further about any of the topics I've covered today.
Thanks again, Simon. So just maybe last call if there are any questions. Then indeed, thank you again.